And I have the last speaker set up. So the last talk for today is going to be given by Iason Marmanis, titled Model Checking C, C++ with Mixed-Sized Accesses.
Hi, okay, can you hear me? Perfect. Hi, I'm Iason, and today I will present our work on model checking concurrent programs that use mixed-size accesses. This is joint work with Michalis, Kokologiannakis, and Viktor Vafeiadis. So as you know, concurrency is when you have a number of threads, and these threads interact with each other. And for example, with shared memory concurrency, they read and write on the same variable. And concurrency is in general hard to reason because of the non-determinism induced by the scheduling. So at each point, you don't know which thread is gonna run. And also, it can get even worse because of weak memory behaviors. So you cannot really reason by interleavings of threads. But it's very important to be able to reason about concurrent software because this is used by critical software, for example, by operating systems such as the Linux kernel. And let me show you an example from the Linux kernel of a data structure that you would like to be able to verify and reason about. And this is the lockref. It's a reference counter, so it's pretty much a lock with a counter that you increase. And on the left, you can see how is the data structure. So it's pretty much a union of two things. It's either 8 bytes, an 8 bytes variable, 64 bits of a lock count, along with a structure that is it's two variables of 4 bytes, a lock and a count. So for anyone who doesn't know, union is like the same data you can see it in two different ways, either 8 bytes or 2 times 4 bytes. And on the right, you can see a method that is increasing the reference counter. And what this does pretty much in the first part with the yellow is a fast path. So it's trying to read the whole thing as 8 bytes. And if it sees that the lock part is not taken, it's trying to increase the counter at once with this cas concurrent swap operation. And if it does so perfect, it returns nothing else to do. Otherwise, it's falling back to the slow path. So it's trying to take the lock, so access just the lock part of the 8 bytes, so only 4 of them. Then increase the counter, so access the other 4 bytes. And then again access the lock by releasing it. And this pattern here is called mixed-size accesses. So you're accessing the same 8 bytes in different ways, either the whole thing or the first 4 bytes or the other 4 bytes. So to verify in general concurrent programs, one such technique would be stateless model checking. And it's good because it handles concurrency, it is automated, and it also handles weak memory behaviors. But unfortunately, you cannot use it right now to verify a program such as the previous one because it cannot handle mixed-size accesses. So our contribution is Mixer, a stateless model checking algorithm that handles mixed-size accesses. It's complete, so it explores every behavior that the program can give you. It's optimal. I'll discuss more about what this means later. It only uses polynomial space, so it's really stateless. And we also have a tool implementation that we use to verify some clients of the lockref data structure. So before going to the problem, I need to give you some background on stateless model checking. So as I mentioned before, it's an exhaustive exploration. It's trying to, you give it a concurrent program, it's trying to explore every trace that the program can give you. And as an example, you have this program here with 3 threads. The first one is writing 1 to x, the second is writing 1 to y, the third thread is just reading x. And stateless model checking would give you the 3 factorial, the 6 traces that you get. But of course, this doesn't scale. As you can see, it's the state space explosion problem. The more you increase the size of the program, the more exponentially the number of traces increases. So stateless model checking is usually combined with a technique called dynamic partial auto reduction, or DPOR. And what this does is it's based on the observation that instructions often commute and you don't really need to consider every trace. The state of the art, instead of actually exploring traces themselves, it explores partially ordered traces. So only the orderings that are really necessary. And these are called execution graphs in the literature. So here you can see the two graphs that this program corresponds to, and they only differ in what the read reads from. So the middle thread, it's immaterial, so you don't need to order it with anything. So just to see how the execution graphs look, you might have heard from the talk before, but let me repeat. So it's a graph. It consists of a set of nodes. Each node corresponds to an instruction. So the write 1 to x corresponds to this write x1 node here. And with the green node, with the green arrow here, the arrow, it's just the order where it's just an order that says where does the read from. So on the bottom, it reads from the leftmost node. It reads 1. And I'm assuming the initial value of 0, so I'm omitting any edges that come from the initial values from the initial write. So how does the state-of-the-art DPOR work? How does it explore these execution graphs? So it does so incrementally. So again, with the same program, I'll show you a simple run. It starts with the empty graph, then it executes the leftmost instruction. This is random, but I'm assuming every time that you execute the leftmost thing that exists. So you're adding the write, then you're adding the second write, so you're in the third graph here, and now you have two choices. DPOR has two choices. You're adding a read, it can either read 0 or it can read 1. So it will branch out and give you the two execution graphs, and that's perfect. So let me show you, make it a tiny bit more complicated to show you another feature of DPOR that's very important. It's the same program on the bottom, I'm just moving the first instruction at the end. So the write 1 to x goes at the end. So again, you execute the two first instructions. Now the read can only read 0, nothing to do. And here you're about to execute the write 1 to x. Now you again have two choices. Either just execute it, do nothing else, and this is the top execution graph that you see, or add it and revisit the previous read. So you need to give the read the choice to read from a write that was added later. And you can see this with the edge there. Now the read is reading from the later write. This is called the revisit. It's very important how DPOR works. Two more things about DPOR that I want to mention is that you in general want to only explore consistent executions. So in general, you can create execution graphs that don't really make much sense. They might have some cycle that's prohibited. If you're assuming sequential consistency, there is no trace that can explain it. So there is a consistency predicate that tells you whether a graph makes sense or not, and you care about it. And another thing you want from these algorithms is to be optimal, which means that you're not getting any graph more than once. You get exactly the two graphs that, in this example, you get exactly two graphs, no more. And one key assumption for DPOR to work that I want to mention, will be useful very soon, is extensibility, which says that given a graph that you have reached and the graph is consistent, and then one more instruction that you could have executed, so one pending instruction, there is a way to add the instruction to the partially ordered trace and remain consistent. Small example, one thread, two instructions, write 1 to x, read x. You have the execution graph with just the write. Well, you can add the read and make the read 1. That's consistent, perfect. But you could have also added to read 0, but this is not consistent. So any coherent model will tell you that this doesn't make sense. So this is not consistent. All right, now I'm almost getting to the problem. Why it's not trivial? What's the problem with mixed size access and DPOR? So how would you do it? So the first thing you would have thought would be to take the mixed size access, break it into multiple accesses. So the lock and the ref lock, the 8 bytes access, break it into 2. Or here the 2 byte accesses of that. So this is an instruction that just writes 1 and 1 to both bytes of x. X has 2 bytes. So you could just break it into 2 accesses, write to the first byte, write to the second byte. But unfortunately, this doesn't work. And the problem is that you're creating executions that are not extensible. So take this program, for example, 2 threads. The first one is writing 2 to the first byte of x, and then reading the second byte. And the second thread is the instruction on the top, just writes 1 to both bytes. So DPOR would end up in the execution that you see here, where the rightmost write is ordered before the write on the left. This is with this big edge here on top. And pretty much what this means is that the access of the second thread is ordered before both instructions of the first thread. This is consistent, fine, but there is no way to complete the graph, to complete the execution and not the second access. And to see why, in the first graph, you're pretty much ordering the second thread before everything. So now you cannot add the write 1 to the second byte because the read must have read 1, not 0. So extensibility breaks and DPOR fundamentally doesn't work because of this reason. So our solution mixer works under the following observation, is that yes, you don't have extensibility in the access level, but you can still assume extensibility at the instruction level. So what this means is that if you're not executing instructions half, like some accesses, you can fully execute one instruction at each point. So before you would have executed the first thread only, and now you can one thing you can do is just add the missing instruction at the order after the first thread. And this means that the first graph is extensible. Fine, but this is not so simple, unfortunately. And you can see this with a very simple example. 3 threads. The first thread is reading both bytes of variable x. The second thread is writing 1 to the first byte. The third thread is writing 1 to the second byte. And the question is how to read the execution, whether the read reads 1 for both. And you would assume that you would get there by, again, if you think that you're executing the program left to right, you would just add the read, then add the second write, do a revisit, make it read from this write, and then do one more. And you would think you would get there, but actually you don't. What you get is the execution where the read only reads from the rightmost write. And the reason for this is how this kind of DPOR algorithms work. So what they do when you revisit is that you remove all the events, all the nodes that were added after the read and are not the write or something that the write depends on. So they would get you to the execution there, which is not what you want. And going forward, you also cannot reach the graph that you want, so you would miss it. Our solution to this is a new kind of revisit procedure that we named the multi-write revisits. So when you're revisiting a read from a write, you also have the choice to have a set of writes, the keep set, that it would have normally been removed from the execution because of how DPOR works, but you actually don't. So here, from the execution where the read reads from the middle write, you have the choice to take one revisit step, and keep the middle write, so don't remove it. And they together, with the write that you're about to add, revisit the first read, and you get the execution that you want. Fine. This adds a lot of more things that the algorithm can do, so a lot more execution graphs. And there comes a problem, how do you know you're still optimal? So this is the whole difficulty. And to see why, how could this happen, consider another execution that the DPOR would reach, which is the read reading from only the rightmost write. And here you would again do the exact symmetric thing. Add the middle write, keep the other write, revisit together, get the same execution. So your algorithm wouldn't be optimal anymore. So for this, we need a bunch of conditions that we've added, and one of them is tie breaking. So tie breaking would it has a way to tell which of the revisit steps of these two you allow, and we also have some more conditions to guarantee that to do a revisit, there is a unique choice of keep sets that are allowed to do it. So this is how we guarantee optimality. Okay, so moving on to the evaluation, we implemented a mixer on top of an open source tool, GenMC, and we used it to verify clients of the Lockrev implementation from the Linux kernel. And here we have one parametric client that is parametric to the number of threads, and we managed to run the tool to verify it for up to 4 threads before timing out at 30 minutes. And the reason for this is, as you can see, the executions grow very fast from some to hundreds to tens of thousands. And finally, we also observed that when running Mixer to benchmarks that do not use mix size access, you're only introducing some moderate overhead over the state of the art, so a bit less than ×2. And just to recap, I presented Mixer, a DPOR that handles mix size accesses. It's complete optimal, it uses polynomial space. It does so by a new kind of revisits that we introduce, the multi-rate revisits. And in the paper, you can see a sketch of how you would extend this algorithmic framework to support a larger class of programs, so transactional programs. So mixed size access, you can see them as a transaction that does all the accesses with some atomic semantics. And that's all I had. Thank you very much.
Any questions? Okay, let's start here.
Hi. So can you go back to the slide where you explained the keep sets? Yeah. So am I missing something? But these, why does this not happen? Because they are unique. These are not the same. The case.
So, sorry, could you repeat it? Why the are the same?
So why is the second one? Why does the second one not happen? Why do you have optimality? You say that you need to have unique K for each revisit, but these are unique. These are different.
Yes. So there are two conditions: type breaking and being unique, which is a bunch of conditions I don't have space to add. So type breaking works in the following way: first, you force the scheduler to only execute left to right, and then only allow keep sets that are on the left of the final write that does the revisit. So that's why you allow the top revisit, but not the second. Thank you.
Over here.
I've been thinking about similar stuff, and I was wondering, because one of the ideas I had...
Sorry, can you...
Okay, sorry. I was thinking about similar stuff, and one of the ideas I had was to keep the writes together, but break up the reads. Is it a technique that you have considered, or not?
So I think the problem with that, and many of the problems that you would get, is with the read-modified write operations. So I don't think this would help at this point. So even if you split the reads, as soon as you've added the reads in some way, they're ordered before some instruction that is a read. Imagine, like similar to here. So imagine that the second thread here, just this NRMW, it reads something that forces it to be before the leftmost read. You cannot close RMW, and this wouldn't matter if split the write or don't split it. Does it make sense?
Not completely, but maybe we can talk.
Maybe I can chat on and write you the example.
Hi, I'm a bit confused about which memory model you've been using, because as far as I understand, it's undefined behavior in C++ to do mixed-sized accesses, because you would have to do nasty casts that violate the object model. So how can I don't think you can even write code that would do this. I mean, the Linux kernel does their own weird stuff, which is not the actual C++ memory model. But outside of that?
Yes, it is undefined behavior. We're assuming some release acquire, but the framework in general is parametric to the memory model. I didn't want to discuss about it. I'm assuming a C here. But so you can use it for your memory model that you have at hand, supposedly that you have some semantics, like it's not undefined behavior. So you could have used it for the Linux kernel.
Okay, I'll ask now, but more later, thanks.
Any other question? So maybe I have a small one or a couple of small questions. I remember seeing another paper in the last year or two, I believe in Atlas, kind of targeting mixed-sized accesses, even building on top of GenMC, I think. Is this in your radar? Can you compare your technique to that?
I know about so they discuss a lot about the implementation part. As far as I understand the paper, they don't change anything else, so they should have hit some counterexamples that we have. So I'm not completely sure that I understand correctly, but if they haven't changed anything significantly, probably they would have hit some bug. But
okay. And then
But maybe I don't understand it completely, so I don't want to say much.
And here you said you assumed SC accesses on the independent kind of bytes?
In the presentation, yes.
In the presentation.
The implementation is some release acquire plus RMWs.
I see, okay. And are you enumerating RFs or RFs NMOs?
RF-NMO.
RF-NMO.
Yeah.
And do you expect the consistency equation for RF to become any more difficult now with these mixed-sized accesses for release acquires?
Like if you don't have MO.
Yeah. So normally it's an easy problem to solve computationally for release acquire. But now that you have these multiple RF edges, does it make the problem any more difficult?
I haven't thought about it, honestly, so okay. I'm not sure.
All right. Any last questions? Okay, let's thank Iason again.